Cross product. In order to make it easy to compute a cross product, it's nice to know how to compute a 3x3 determinant. So let's go over that really quick. By a 3x3 determinant, I mean a computation that we do on a 3x3 matrix. So here we have an array consisting of 9 numbers, 3 rows and 3 columns, A1, A2, A3, B1, B2, B3, and C1, C2, C3. The lines to the left and the right of these numbers indicate we're going to take a determinant. The computation for a determinant is a little complicated, but if we follow a certain pattern, we could get it fairly easily. Notice I rewrote the first 2 columns to the right of the line. This is just to help us initially to compute the determinant. In practice, you won't have to do this after you get a little experience. Okay, so over here, we see that the definition of the determinant is a little bit complicated. We have a bunch of products and we're adding and subtracting those at various times. Let's see how we do it. We first start by going down each of the 3 diagonals from left to right. I've drawn those in purple. And as we do that, we multiply the numbers together. So we multiply A1 times B2 times C3. Then we multiply A2 times B3 times C1 and A3 times B1 times C2, and we add all those up. Now we do the same thing going down the reverse diagonals, but this time we subtract each time. So we have minus A3 B2 C1, minus A1 B3 C2, and minus A2 B1 C3. So adding up those 6 terms gives us the determinant of a 3x3 matrix. Now, I'll just mention this is just one of many ways to compute a determinant. Another common way is by using what's called a cofactor expansion. I'm not going to go over that method here because we'll only need to compute 3x3 determinants, and this is a nice shortcut method for doing that. Okay, so now's a good time to try an example just to make sure you understand how to compute a determinant. And as always, you should pause the video, try this example yourself, and then resume the video to check your answer with mine. Okay, so let's compute this determinant. So we have 1 times 5 times 4 is 20. And then 2 times 0 times 2 is 0. Notice how I wrapped around as I went down that diagonal. 2, 0. And then instead of having drawn the column, I just wrapped around to the lower left-hand side. I'll do the same thing here. 3 times 4 times -1 is -12. Now going backwards, we have 3 times 5 times 2 is 30. We're subtracting that one. And then we have 1 times 0 times -1 is 0. And finally, 2 times 4 times 4 is 32. And again, we're subtracting that one. Combine all these numbers to get the answer of -54. Okay, now we're ready to define the cross product. So let U and V be 2 vectors in 3 space, U with components U1, U2, and U3, V with components V1, V2, and V3. Okay, the cross product of U and V, written U cross V with an X, is equal, and I put the equal sign in quotes because this is more of a mnemonic device for remembering the definition rather than a precise definition. Notice we're taking a determinant of a matrix, but the matrix has as its first row vectors I, J, and K, and the other 2 rows are real numbers consisting of the components of U and V. That's not a real determinant because to do a determinant, the objects inside the matrix should all be the same. Nonetheless, as a mnemonic device, it still works. It gives us what we want. So if we write everything out, we see we get U2 V3I, and then going down the second diagonal, we have U3 V1J. The third diagonal gives us U1 V2K. And then going backwards, we have minus U2 V1K, minus U3 V2I, and minus U1 V3J. Okay, now just combining the I's together, the K's, and the J's together, we can write it like this. U2 V3 minus U3 V2I plus U3 V1 minus U1 V3J plus U1 V2 minus U2 V1K. Some people like to reverse the terms in the middle for the j component and put a minus sign. It's the same thing. But the reason for this is if we were to do a determinant by a cofactor expansion, this is how it would come out. Either one of these is okay. They all are equal to the same thing. Okay, now's a good time to try some examples. Once again, pause the video, try these examples yourself, and then resume the video to check your answer with mine. Okay, so let's take the cross product of these two vectors, u and v. So we form this matrix, ijk, and then we put the components of u, 4, -2, 5, and then the components of v, 5, 1, -1. And we're going to take this determinant. Okay, so for the I component, we have -2 times -1i, or 2i, and then going the other way, minus 5i. For the j component, we have 5 times 5 is 25, minus 4 times -1, so that becomes plus 4. And for the k component, 4 times 1 is 4, minus -2 times 5 is plus 10. Okay, so when we combine these, we get 2 minus 5 is -3, 25 plus 4 is 29, and 4 plus 10 is 14. So the final vector is -3i plus 29j plus 14k. Okay, next, let's show that v cross v is 0 for any vector v. Okay, so let's take v cross v. We put in ijk, and then the components of v, let's assume those are v1, v2, v3, and we write those twice for the second and third rows of the matrix. Okay, so when we write this out, we have v2, v3i minus v3, v2i, right? And for the j component, we have v3, v1 minus v1, v3. And for the k component, we have v1, v2 minus v2, v1. And we see that all three components wind up being 0, so we wind up with the 0 vector. Okay, third one, show that u cross v is orthogonal to u. Okay, we'll need a little space for this. So to show that u cross v is orthogonal to u, we're going to take the dot product of u with u cross v, and we are hoping that that comes out to 0, right? So we'll take u dot, and then we'll just write out what u cross v is. If you need to, you could rewrite that determinant to write this the correct way, or you could just remember the actual definition. I recommend doing it by a determinant. Now, u, remember, is u1, u2, u3. So when we take this dot product, we get u1 times the coefficient of I plus u2 times the coefficient of j plus u3 times the coefficient of k. Now we distribute the u1, u2, and u3 to get u1, u2, v3 minus u1, u3, v2 plus u2, u3, v1 minus u2, u1, v3 plus u3, u1, v2 minus u3, u2, v1. And now notice that the first term and the fourth term have the same factors, but they're opposite in sign. Similarly for the second term and the fifth term, and the third term and the sixth term. Everything cancels out and we get 0, showing that those two vectors, u and u cross v, are orthogonal. Okay. Similarly, u cross v is orthogonal to v as well. A similar computation will show that. So the cross product is nice because it gives you a vector which is mutually orthogonal to two given vectors. Okay, let's go over some properties of the cross product. U cross v is the negative of v cross u. So the cross product is not commutative, but it is anti-commutative. When you interchange the two vectors in the cross product, you get the negative of the original answer. Okay, u cross v plus w is u cross v plus u cross w. This says that the cross product is left distributive over addition. The next one says that the cross product is right distributive over addition. U plus v cross w is u cross w plus v cross w. Similar to with the dot product, we can handle scalars in different ways and get the same answer. K times U cross V is KU cross V, and it's also U cross KV. So we could either take the cross product first and then multiply by the scalar, or we can multiply either vector by the scalar first and then take the cross product. We will get the same answer. U cross 0 is equal to 0 cross U is equal to 0. So the cross product of any vector with 0 is the 0 vector. U cross U is equal to 0. U dot U cross V is equal to 0. In other words, the cross product of U and V is orthogonal to U. And V dot U cross V is 0. In other words, the cross product of U and V is orthogonal to V. Now, we already provided proofs of the last three of those. Well, technically not the third one, but we did the two before it, and the third one is very similar to the second one. You may want to pause the video now and try to prove the rest of these. Write out arguments for the rest of these, similar to what we did for the ones we just did in the previous example. Okay, let's try another example. Once again, pause the video, try this example yourself, and then resume the video to check your answer with mine. Okay, let's find a vector orthogonal to the vectors u, which is 1, 2, negative 2, and v, which is 3, 0, 1. So we're just going to take the cross product of those two vectors. Okay, so for the I component, we get 2 minus 0, which is 2. For the j component, we get negative 6 minus 1, which is negative 7. And for the k component, we get 0 minus 6, which is negative 6. So we wind up with 2i minus 7j minus 6k. Let's just check that the cross product of u and v is actually orthogonal to u. So let's take u dot u cross v. So we have 1 times 2 is 2, 2 times negative 7 is negative 14, and negative 2 times negative 6 is positive 12. Add those up, and we do, in fact, get 0. And similarly, let's check that the cross product of u and v is orthogonal to v. So we have 3 times 2 is 6, 0 times negative 7 is 0, and 1 times negative 6 is negative 6. Add these up, and once again, we do get 0. Okay, it's definitely worth mentioning that the vectors I, j, and k have a nice way to compute the cross product by using this little cycle diagram. I cross j is equal to k. J cross k is equal to I, and k cross I is equal to j. Just follow the arrows in that little cycle diagram to generate these cross products easily. Now, using the anti-commutativity of the cross product, we have that j cross I is negative k cross j is negative I, and I cross k is negative j. So when you go in the reverse direction from where the arrows are pointing, you wind up with the negatives of the answers. And it's also worth mentioning one property that the cross product does not have. It is not associative. So when you do cross products of multiple vectors, you do have to put in the parentheses. Otherwise, it is not clear which ones you do first. Okay, u cross v cross w is not equal to u cross v cross w. Okay, it's time for a big theorem about the cross product. So we're starting with two non-zero vectors u and v. And we're going to show that the length of u cross v is the product of the lengths of u and v times the sine of theta. The area A of the parallelogram that has u and v as adjacent sides is the length of u cross v. And the cross product of u and v is 0 if and only if u is parallel to v. Okay, let's go through part A. So starting with the right-hand side, length u times length v times the sine of theta, let's begin by rewriting sine theta in terms of cosine. To do that, we'll start with the main Pythagorean identity, cosine squared theta plus sine squared theta equals 1, and let's solve that for sine theta. So we could first subtract cosine squared theta from each side to get sine squared theta is 1 minus cosine squared theta, and then apply the square root property to get sine theta is plus or minus the square root of 1 minus cosine squared theta. Now remember that when we're talking about the angle between two vectors, we are always taking the angle that is between 0 and pi. and therefore the angle is in either the first or second quadrant, so sine theta must be non-negative. Okay, so that means we can replace sine theta by just the positive square root of 1 minus cosine squared theta. Again, we reject the negative square root because theta is between 0 and pi, and therefore sine theta is greater than or equal to 0. Okay, now we can use the theorem about the dot product to replace cosine theta by u dot v over length u times length v. And since it's cosine squared theta, we square each factor written there. Okay. Now let's simplify the expression under that square root a little bit by getting a common denominator. We can rewrite 1 as length u squared, length v squared over itself. And now that the denominators are the same, we can combine the numerators to get length u squared, length v squared minus the square of u dot v over length u squared, length v squared. Okay, and finally, the denominator, the squares cancel with the square root to give us 1 over length u, length v. So the 1 over length u, length v cancels with the length u, length v to give us just the square root of length u squared, length v squared minus the square of the dot product of u and v. Rewriting that expression in component form, right, replacing u by the vector u1, u2, u3, and v by the vector v1, v2, v3, we get this complicated looking expression, right? The square of the length of u is u1 squared plus u2 squared plus u3 squared. Similarly, for the square of the length of v. And u dot v we could write as u1 v1 plus u2 v2 plus u3 v3. Now we want to change the form of this so we can recognize it as a length of a cross product. So it turns out that this is equal to this expression. Now, there's nothing going on here more than a lot of tedious algebra. So I'm going to leave this for you to check carefully. You may want to pause the video now and multiply out both of those expressions under the square roots and just check that they are actually equal to each other. To go from the first expression to the second one, without knowing that they're equal is a little bit tedious and takes a little bit of cleverness and regrouping things in the proper way. But luckily, that's not necessary. We know what we want to try to get to. So if we just write down what we want to try to get to and then check that they actually are equal to the same thing, that is good enough. Okay, so as we can see there, that expression is actually equal to the length of u cross v, because the expressions in parentheses there are exactly the components of u cross v. Okay, let's go to part B, that the area A of the parallelogram that has u and v as adjacent sides is the length of the cross product of u and v. Let's start by drawing a picture of two vectors u and v and form the parallelogram that those are the adjacent sides of. Now, what we're most interested in finding here is the height, right? Because the area of a parallelogram is the base times the height. Now, let's pull out a little triangle from this picture where the sides have length of v and the height has length h. And I also labeled the angle there, the angle theta. Okay, using the fact that sine theta is opposite over hypotenuse, we have that sine theta is the height divided by the length of v. Okay, so that means that the height is the length of v times sine theta. Okay, so let's put that back into the original picture. Notice I labeled the height with length v sine theta. I also labeled the lengths of the two vectors, length v and length u. And now just using the basic formula from geometry that area is base times height, well, the base is length u, and the height, according to the picture and what we just found, is length v sine theta. Okay, and by part A, that is equal to the length of u cross v, which is what we were hoping to get. Okay, part C, u cross v is 0 if and only if u is parallel to v. Well, u cross v is 0 if and only if sine theta is 0 from part A. Just to clarify that, the only way that u cross v is 0 is if its length is 0. And similarly, if the length of a vector is 0, then the vector must be 0. And the length of u and the length of v are both not 0, right? Because u and v were given not to be 0. So the only way that u cross v could be 0 is if the right-hand side is 0, and the only way that could happen is if sine theta is 0. Okay, so u cross v is 0 if and only if sine theta is 0. And when is sine theta 0 for angles between 0 and pi? Only at 0 and pi. So this happens if and only if theta is 0 or theta is pi. And both of those are the two cases where u and v are parallel. Okay, when theta is 0, the vectors are pointing in the same direction. And when theta is pi, the vectors are pointing in opposite directions, but still parallel, of course. Okay, let's try an example. Again, pause the video, try this example yourself, and then resume it to check your answer with mine. Okay, find the area of the triangle determined by these 3 points. Okay, so given these 3 points, we want to find 2 vectors. So, for example, we could let u be the vector p1, p2, which we get by subtracting coordinates. 2 minus 1 is 1, so that's the I component. 3 minus 1 is 2 for the j component, and 4 minus 1 is 3 for the k component. We need one more vector. Let's use v equals the vector p2, p3. So we subtract 3 minus 2 to get 1i, 0 minus 3 to get negative 3j, and negative 1 minus 4 to get negative 5k. We could have also used the vector p1, p3 if we wanted to, but we only need 2 vectors. So these 2 will suffice. Okay, we're going to go ahead and take the cross product of these 2 vectors. Okay, put it into our matrix to take the determinant. So for the I component, we get negative 10 plus 9 is negative 1i. For the j component, we have 3 plus 5, which is 8. And for the k component, we have negative 3 minus 2, which is negative 5k. Okay, so the area is 1/2 the length of u cross v. It's 1/2 because it's a triangle, and the area of a triangle is 1/2 the area of the corresponding parallelogram. Okay, so we have 1/2 the length of the vector we just found, negative I plus 8j minus 5k. So that's 1/2 the square root of the square of negative 1 is 1, the square of 8 is 64, and the square of negative 5 is 25. So that's 1/2 root 90. We could split 90 into 9 times 10, so we could split the square root of 90 into root 9 times root 10. So we have 3/2 root 10 square units. Okay, we want to talk about one other type of product called the scalar triple product. It's related to the cross product only in that we're going to use a determinant to compute it. The definition of the scalar triple product is u dot v cross w. And actually, we don't need parentheses there because only one way of doing this computation makes sense. If you try to do u dot v first, you get a scalar. And the cross product operates on 2 vectors, so that doesn't work. So you have to take v cross w first to get a vector, and then u dotted with that will give you a scalar. It's called the scalar triple product because it gives us a scalar as the answer, and the triple because there are 3 vectors involved. Now, it turns out that the scalar triple product can be computed just by doing a simple determinant, by putting the 3 vectors in a matrix, more precisely the components of the 3 vectors. Okay, so let's try an example. You may want to use the shortcut definition of the determinant to compute this. Pause the video, try it yourself, and then resume the video to check your answer with mine. Okay, compute the scalar triple product of these 3 vectors. So I'm going to go ahead and put the components into a matrix, 3, negative 2, negative 5, 1, 4, negative 4, and 0, 3, 2. Okay, so 3 times 4 times 2 is 24. Negative 2 times negative 4 times 0 is 0. Negative 5 times 1 times 3 is negative 15. Now going the other way, negative 5 times 4 times 0 is 0. 3 times negative 4 times 3 is negative 36. We're subtracting, so it becomes positive 36. And negative 2 times 1 times 2 is negative 4. Again, we're subtracting, so it becomes positive 4. Add these all up, and we get 49 for our answer. Okay, let's finish with a theorem about the scalar triple product. So we're starting with 3 non-zero vectors, u, v, and w. The volume V of a parallelepiped that has u, v, w as adjacent edges is the absolute value of the scalar triple product of u, v, and w. Now, the scalar triple product is 0 if and only if all 3 vectors lie in the same plane. And the last two allow us to do some funny things with the dot and the cross. In part C, we see we can rotate the vectors UVW to WUV or to VWU, and we get the same answer. And part D says we could interchange the dot and the cross, and we get the same answer. Okay, let's start with part A. So first of all, what is a parallelepiped? We get a parallelepiped by taking 3 arbitrary vectors and starting them at the same initial point, and then drawing the parallelograms that are formed from each of the sides, right? So a parallelepiped has a parallelogram base and parallelogram sides. If the vector u was perpendicular to the base, then we would actually get a prism whose base was a parallelogram, but parallelepipeds do not have to be prisms. Okay, so to compute the volume of the parallelepiped, we need to find the area of the base times the height. Well, the area of the base, that's just the area of a parallelogram. We already know from the previous theorem that that's the length of V cross W. We need to find the height. The height we could see in this picture as this black vector. And notice that the height is the distance between the 2 bases. Right? So how do we get that? Well, it's hard to get h directly, but we could find a vector that is perpendicular to the base simply by taking the cross product of v and w. Remember that the cross product of v and w is orthogonal to both v and w, and therefore it's orthogonal to that parallelogram formed from the sides v and w. Okay, now, once we have that, how do we change that to the vector whose side has length h? Well, we could take a projection. We're just going to project the vector u onto the vector v cross w. And we have a nice formula for that. That's u dot v cross w over the length of v cross w times a unit vector in the direction of v cross w, namely v cross w divided by the length of v cross w. And now we could use the basic property of the length of a vector. When we have a constant times a vector inside, we could pull the constant out by putting it in absolute values. So we can rewrite the length of that second expression there as the absolute value of the scalar triple product divided by the square of the length of v cross w. And notice that we have the length of v cross w twice in the numerator and twice in the denominator. So they cancel, and we're left with the absolute value of the scalar triple product, which is what we wanted. Okay, part B, u dot v cross w is 0 if and only if u, v, and w lie in the same plane. Well, u, v, and w lie in the same plane if and only if the parallelepiped with these vectors as adjacent sides has volume 0. If and only if the absolute value of the scalar triple product is 0. And remember that the absolute value of a number is 0 if and only if the number itself is 0. So the absolute value of u dot v cross w is 0 if and only if u dot v cross w is 0. Part C, u dot v cross w is w dot u cross v is v dot w cross u. Okay, now put this proof in quotes because there's one fact I'm going to steal from linear algebra, and that's that 2 row interchanges of a matrix do not change the determinant of the matrix. I'm going to use this fact freely. It's not too hard to prove using methods from linear algebra, and it's especially not too hard to prove using a 3x3, but I don't want to take us outside the scope of what we're doing here. So using this fact that 2 row interchanges do not change the determinant of a matrix, all we have to do is recognize that we can get a rotation by doing 2 row interchanges. So if we interchange rows corresponding to u and w, we get WVU. And then if we interchange the rows corresponding to V and U, we get WUV, right? So in other words, U dot V cross W is W dot U cross V. And we get the second equation there either by doing exactly the same thing or just doing a substitution of variables. Okay, and for part D, U dot V cross W is U cross V dot W. This follows from what we've already done very quickly. U dot V cross W is W dot U cross V. That's exactly part C, the first equation in part C to be specific. And now we could interchange W and U cross V because the dot product is commutative.